So today we're going to look at energy and light equations. So we just talked about how to read the Bohr model of the hydrogen atom. Today we're going to look more in depth at light and characteristics of light. And so we have light wave, just like any other kind of wave. It goes like this, right? And you have crests and troughs and things like that. And then so we have the wavelength. By definition, it goes from crest to crest or trough to trough. This is the wavelength. And we use the symbol lambda to represent the wavelength. Okay? And so wavelength is how long the wave is. If the wave is very small, right, the wavelength will be much shorter, right? So then frequency is another term that we have, and frequency is how fast the wave moves, the rate at which the wave moves. It's the number of waves that pass through a point per second. And so if we have a long wavelength, the frequency would be, excuse me, the wavelength is high, the frequency would be very low, or be very slow, right? If we have a shorter wavelength, the frequency would be much faster. So as the wavelength increases, the frequency decreases, right? These are inversely proportional. Okay? And they're inversely proportional to the speed of, based on the speed of light. And so the equation we get is that the speed of light is equal to lambda times the frequency. So again, we use lambda for wavelength and this mu for frequency. It's sort of like a V and a U combo. So again, if we go back to our reference tables, we look at our electromagnetic spectrum, which is just underneath our Bohr model. Okay? Our Bohr model only shows us three types of light: visible, UV, and IR. So if we look here, we'll find we have gamma rays have very short wavelengths. Okay, 10 to the minus 13. That's very, very small. Then we have X-rays, ultraviolet, infrared, microwaves, and radio waves. Radio waves being very large, 10 to the 4th. And these are measured in meters. Okay. It also helps us and breaks out our visible light, so it shows us that red, orange, yellow, green, blue, and violet, Roy G. Biff, is in the order of larger wavelengths to smaller wavelengths. Okay. So your spectrum is on your reference packet, so you don't have to memorize it. Okay. The speed of light, however, is a number you're going to need to memorize, and that's going to be 3.0 times 10 to the 8th meters per second, or 3.0 times 10 to the 10th centimeters per second. Right? But really, we'll probably use it mostly in meters. Right? Our equation that we're going to use, I already gave it to you here, so I'll just rewrite it over here, is the speed of light equals the wavelength times the frequency. Right, so what's the frequency of light that has a wavelength of 450 nanometers? Well, if our wavelength is 450 nanometers and our speed of light is in meters, that's not going to work. We can't have unlike terms, so we must convert one or the other. I like to convert things to the base unit, that's just me. And so we're going to convert 450 nanometers into meters. So our nanometers need to go on the bottom, our meters on the top. 1 meter has 10 to the 9th nanometers. Right? And so we'll end up with 450 times 10 to the 9th. Oops, negative 9th. Which, if we write in correct scientific notation, would be 4.5 times 10 to the minus 7. Okay. So what kind of light would that be if it has a wavelength of 4.5 times 10 to the minus 7? Well, 4.5 times 10 to the minus 7 would fall right here, that's 4.2, and that's 4.9, and so that would be blue light. But that's not the question asked us, so we want to know what is the frequency. And so we take our speed of light, 3 times 10 to the 8th meters per second is equal to the wavelength, 4.5 times 10 to the minus 7 meters times our frequency. And so then we're going to divide 4.5 times 10 to the minus 7 . And we find that our frequency is, now when we do these in our calculator, I'm going to show you an easier way. Hopefully you can see the yes. And so what we're going to do, move this up so you can see what I'm punching in the calculator here. We're going to do 3. Then we see this EE button right here is above your comma. You can do second, comma, and then your exponent, 8, divided by 4.5, that EE again, and then your exponent minus 7. And then that tells us that our frequency is 6.7 times 10 to the 14th. Now the units for frequency we can write as in 2 different ways. As hertz, which is an Hz, or per second, per s per second. Okay, either one of those is the unit for frequency. And again, frequency is the rate at which the wave moves. Okay. So next we're going to look at calculating energy. So we calculate energy using a different equation. Energy is equal to Planck's constant, which you won't find in your reference packets because this is our step up for honors. 6.626 times 10 to the minus 34 joules per second. Alright, and so our equation is energy, which is measured in joules, is equal to Planck's constant times our frequency. Remember, frequency is per second. Alright, so we calculate what's the energy of light that has a wavelength of 450 nanometers. Well, that was the same problem we just had a minute ago, right? And we found that the frequency was 6.7 times 10 to the 14th. Right? And so our frequency is 6.7 times 10 to the 14th hertz, or per second. Alright, and so we calculate our energy by taking our Planck's constant times our frequency, and we'll get the number of joules for our energy. And we get 4.4 times 10 to the 12th joules. Okay. So you go ahead and do the next problem. Again, remember, we first found the frequency. So keep in mind that we have 2 equations. Energy equals Planck's constant times the frequency, and the speed of light equals wavelength times the frequency. So to calculate energy from the wavelength, you're going to need to use both of those equations. We'll go over this problem in class tomorrow.